In this talk, I'm going to present a novel memory reclamation algorithm for concurrent data structures. A concurrent data structure provides fast and non-blocking operations that run in parallel safely. However, designing a concurrent data structure is a complex problem. Among many issues, memory management is a common difficulty. In particular, naively freeing a memory block can lead to memory errors. For instance, suppose a thread holds a reference to a block and sleeps. In the meantime, another thread removes that block from the data structure, and suppose it immediately frees that block. Then, if the first thread wakes up and dereferences the block, the system would crash. To prevent such error, the first thread should protect the block from being reclaimed, and the second thread should defer the reclamation until it is safe. The solution to this problem is called Safe Memory Reclamation, or SMR algorithm. Design and implementation of SMR has been an active field of research. Most of the SMRs, including ours, are based on either of these two SMRs, hazard pointers and epoch-based reclamation. So before we present our work, let's first review how they work and why they are not perfect. Hazard pointers, or simply HP, is probably the most intuitive SMR. To protect a block B, you can simply invoke the function named protect on B. When protect B is called, the other threads will be informed that B is a hazard, a block that must not be freed. So, the reclamation of B should be deferred until B is no longer protected. As in the previous example, suppose T2 removes the block B. So for safety, T2 has to defer the reclamation by calling the function named retire instead of directly freeing the block. The actual reclamation is done later by the collect function. This function is occasionally called to check if a retired block is no longer protected and free it if it is so. So here, collect cannot free B. Later, T1 will unprotect B, and the subsequent collect will be able to free B. Unfortunately, hazard pointers has significant drawbacks. First, it is not fast due to the synchronization cost. HP requires protect and collect function to be synchronized. To do so, both functions should issue a store load fence, which is a very expensive instruction. While traversing the data structure, protect is called for each block, slowing down the operation due to the accumulated cost of fences. Second, HP does not support a wide variety of data structures. Specifically, data structures that retire a chain of linked blocks cannot use HP. For example, suppose T1 is traversing the linked list and it is protecting the block B0. At the same time, T2 removes B0 and B1 and retires both of them. If collect is called at this point, it can reclaim B1. The problem here is that T1 does not know that B1 is already freed, so it will proceed to protect B1. In this case, even if T1 has protected B1, dereferencing B1 is not safe, as it is already freed. Therefore, HP cannot be used for this kind of data structure. On the other hand, epoch-based reclamation, or simply EBR, takes a completely different approach. To get accesses protected in EBR, all you have to do is entering an active state with setActive function. Once you become active, all of the accesses will be safe. The collect function checks whether a retired block can be used by an active thread. If it is, then it should not be freed. So, in this example from the previous slide, both B0 and B1 won't be freed. Then, if T1 exits the active state with the setQuiescent function, there's no active thread referencing B0 and B1, and therefore B0 and B1 can be freed. EBR has two advantages over HP. First, it is faster because the store load fence is needed only once for each setActive function. Second, EBR is more widely applicable than HP. For example, it can be applied to the chain retirement example we saw a while ago. This is because EBR provides a protection for all potential accesses too. But how does EBR know whether a block can be used by an active thread? To decide whether a block is accessible, threads build a consensus using logical timestamps called epoch. To illustrate how the epoch consensus works, let's consider the timeline of each thread. Here, the blue arrows correspond to active state. When T1 becomes active, it is assigned an epoch number, say E. When another thread enters an active state, it will check if it can increase the epoch following the epoch consensus rule. The rule says that the epochs of the concurrent active states may differ by n most 1. So when T2 becomes active, it sees that the only active state is in epoch E, so T2 can increase the epoch by 1. On the other hand, T3 cannot increase the epoch to E plus 2, as T1 is still active in E. Following this rule, we can mark the remaining arrows. Suppose T1 removes the block B and retires in epoch E. Then, the epoch consensus guarantees that B is safe to free at epoch E plus 3. To see why, let's consider which active states may hold a reference to block B. First, thread in E plus 1 might have obtained a reference to B before B is removed. This is because there is no strict ordering between E and E plus 1. On the other hand, T2 at E plus 2 cannot hold a reference to B because epoch E strictly happens before epoch E plus 2. So when T4 calls collecting E plus 3, it knows that E plus 3 does not overlap E plus 1, and the only overlapping epoch, E plus 2, cannot use B. Therefore, B can be freed safely in epoch E plus 3. Unfortunately, EBR also has a significant drawback. Namely, EBR is not robust, meaning that a single non-cooperative thread can block the reclamation of the entire system. Suppose B is retired in E, and T3 does not exist its active state of epoch E plus 1. Then, the entire system cannot reach epoch E plus 3, and therefore, B will never be freed. To solve the problems of hazard pointers and epoch-based reclamation, many SMR algorithms have been proposed. However, most of them has to make a compromise. For example, some SMRs are not compact, meaning that they need metadata for all allocated blocks. Some of them are not self-contained, in that they rely on assumptions about the execution environment, like special features of the operating system. In addition, many of them did not solve the applicability issue, and one was not robust. In this work, we developed a new SMR named Pointer-and-Epoch-Based Reclamation, or simply PEBR. To the best of our knowledge, PEBR is the first SMR to be fast, robust, compact, self-contained, and widely applicable at the same time. PEBR is powered by these three key ideas. First, PEBR takes a hybrid approach of EBR and HP, using a technique called ejection. Ejection is used for making EBR robust. An SMR using an ejection technique provides a method for ejecting the non-cooperative thread from the epoch consensus. The ejected thread is forced to quit its active state, so the other thread can increment the epoch number. In addition, it provides a method for threads to check if it is ejected, so that they can start their recovery procedure. Let's see how PEBR handles ejection. Suppose the block B is retired in E, E2 ejects E3, and calls the collect function in E plus 3. In EBR, it was safe to free B in E plus 3. However, it might be the case that the ejected thread was referencing the block. So, in order to provide protection even after the ejection, PEBR uses the protect function used in hazard pointers. So, even if T2 is in E plus 3, it cannot free B because it is a hazard pointer. In PEBR, the protect function has an additional functionality, namely detecting ejection. If the thread is ejected, the protect function notifies the caller of the ejection by failing. So, by calling the protect function, the thread can detect ejection and start the recovery procedure. Ejection itself is not an entirely novel idea. What is difficult about ejection is how it is implemented. In fact, There are 3 SMRs using ejection in the literature, and all of them suffer from the problems I've mentioned before. On the other hand, PEBR does not have such issues thanks to the remaining 2 key ideas. The second key idea of PEBR is the widely applicable API. Let's look at it in more details. As an example, let's get back to the chained retirement example. We have seen that this example is not supported by hazard pointers because of its inability to detect unsafe protect. On the other hand, it is supported by PEBR because the thread can avoid unsafe protection with ejection notification. To see how ejection notification is used, let's run the same example with PEBR. T3 is traversing the list, and it is protecting the block B0. B0 and B1 are retired in epoch E, and T2 ejects T3, and then calls collect at E+3. V1 can be freed now, because it does not have protection of the Epoch Consensus and the hazard pointers. If T3 calls protect B1 at this point, it will fail, because of the ejection notification. So, T3 will not reference B1 and start its recovery procedure. Therefore, T3 does not suffer from the unsafe protection problem of hazard pointers. But actually, in order to guarantee the total absence of unsafe protect, T3 has to follow this requirement during the recovery procedure. If a thread is ejected, then it must not start the traversal from the previously protected block. In this case, the requirement says that T3 should not traverse the linked list starting from the block B0. You may think that this requirement may restrict the applicability of PEBR, but that is not the case. In fact, data structures based on EBR can be ported into PEBR without violating the requirement. The process is straightforward. First, before each reference, you should protect the block. Second, if the protection failed due to the ejection, then restart the operation from the root of the data structure. By following this process, the user can automatically satisfy the requirement and avoid the unsafe protection. Now, let me explain the last key idea, namely an ejection algorithm that is robust, self-contained, and compact. The main idea is to centralize every synchronization into a single word metadata for each thread. In PEBR, all threads have a status word, which is basically a pointer to their hazard list. But it is tagged with few bits indicating its status. The eject tag tells whether the thread is being ejected, and the active tag tells whether the thread is in an active state. And the epoch tag tells what epoch the thread is in. As all the metadata is on a single word, we can atomically update the status with compare and set instruction. To see how PEBR uses the status word, let's assume that the blocks B0 and B1 are retired at E. First, when T3 enters an active state, it will set the tags of each status. And next, let's suppose T3 calls protect B0. An interesting observation here is that the protection of B0 does not need to take effect right away, because the accesses are already protected as T3 is in an active state. So, instead of adding B0 directly to the hazard list, we can store B0 in a local hazard list first, and publish it later when it gets ejected. So after adding B0 to the local hazard list, T3 will check that it is not ejected. When T2 ejects T3, it first marks T3 as being ejected. Then, it publishes T3's hazard list and marks T3 as inactive. When T3 tries protecting B1 after ejection, it notices that it is ejected, and therefore the protection fails. Finally, let's consider the collect function called at E+3. First, it cannot free B0 because each in the published has a list. On the other hand, it can free B1 because the protection has failed. The key to the safety of PEBR is the strict ordering of ejection and protection. To guarantee such ordering, the functions eject and protect should be synchronized with store load fences. But as I mentioned before, store load fences are expensive. So for better performance, we apply the technique used in modern implementation of hazard pointers. In a nutshell, we can replace the store load fences with a pair of process-wide memory fence and a compiler fence. By using the lightweight compiler fence in the hot path, which in this case is protect, we are able to minimize the synchronization cost. So that was the main idea of PEBR, and let's take a look at some benchmark results. We benchmarked many concurrent data structures using PEBR and compared with the version without reclamation and the version using EBR. In the first experiment, we tested the throughput in normal case. As you can see, throughput of PEBR is close to EBR. In the second experiment, we tested the peak memory usage when there is a non-cooperative thread. First, when there is a stalled thread, EBR was not able to reclaim memory at all. When there was intermittent interference by a non-cooperative thread, or thread oversubscription, the memory usage of EBR was multiplied by several times. In contrast, PEBR was barely affected by any of such interference. We observed that the results are consistent in other data structures. So, that's all I got for today's talk. In the paper, we described many important details of PEBR, including the safety proof and the full evaluation results. Our implementation of PEBR is publicly available on GitHub. Thank you.